Uh, the reason why we fully need to understand the beam theory is that the beam basically being used in real structures a lot. And second, beam structure can be very dangerous. I mean, we need to pay real careful attentions because a lot of high stresses can be uh, caused in beams. So we need to be very careful. Uh, but at the same time, if we just design safely, then we will waste our materials and cost. It's not may not be a cost effective. That is not good neither. So we fully need to understand the fundamental theory, and based on that one, we need to design precisely. To do so, of course, we need to understand the situations. Situation means that what's the material, what is the loading conditions, and what would be the design requirement, and so on. So anyhow, again, I cannot emphasize enough how important the beam theory is. The So chapter wise, we we are covering the chapter 11, beam theory. Actually, the chapter 10, which we cover as an introductions of a beam, that is the mainly the stresses caused by the beam. Uh, Now, chapter 11 is about the beam deflections. Uh, Beam stresses is we start with the deflections, the stresses and fundamental assumptions. Mainly the strain will be caused by the geometric assumptions that we already discussed a lot. Uh, the simple equation wise, epsilon x equal y divided by r. R is the curved. So when beam is subject to a certain moment and load, bend, then this beam is assumed to be curved, assumed to deform with a curvature, and so always there is a center of a radius, and through the beam, the strain is always proportional to thickness direction, but always given as a one radius. That is the most fundamental assumption we studied, and the just one second. So as a continuations of that, the simple beam stress assumption, now today we will discuss about uh, how to calculate the beam deflection when the beam is subject to a certain load. Okay. So deflection due to bending, 어, 밴딩 하중에 의한 처짐, 빔의 처짐을 우리가 배우는 겁니다. So we will study about how to calculate the deflection due to a bending. Now, well, we already slightly review this problem statement, but let's do it again. This is a deflection due to bending. This is a kind of a beam, straight beam, and the subject to several different load. Uh, this could be some distributed load. QX is a distributed load. Okay, distributed load. Simply say QX distributed load is a load per unit length. Okay, load per unit length. So we will pay more attention to a QX. And now what we mean by the deflection is the given as a sort of deform like this. And coordinator we're gonna use is along the beam you're gonna use X, and the vertical direction we're gonna use the Y. And P is the vertical load, again, is a concentrated load. And moment M is the given as the pure moment. The pure moment M is the one we consider in our beam. Okay. Now, in addition to this moment M, we will consider vertical load P and the distributed load Q. That is the additional load. Uh, well, looks like the moment M and P and Q look quite different. Yes, they are quite different because M is the moment and P and Q is the load. But pay attention to the direction these loads are applied. Now, very importantly, on the left-hand side and the right-hand side, we have a BC, boundary conditions. So again, the given is that cross sections and material property of a beam, uh, and material is simply Young's modulus, and the cross section is given as I. So totally, EI is a bending rigidity, which we derived last week, the first part of a beam theory. And then again, as shown in this figure, external load as a function of X, this is important, function of X. We obviously we need to know where these loads are applied, either distributed load or concentrated load. We need to understand where they are applied. So mathematically say we can say function of X. Now, boundary condition for both ends, BC, we will again pay much attention to what kind of boundary condition. And now to find, so what we're gonna find, what we're gonna calculate. First one is the vertical deflections and the bending moments and shear forces. Well, we don't know exactly what it means, shear force and then, deflection. But let's say once we calculate the bending stress, bending moment at any cross section, we already know how to calculate the bending stresses. Bending stresses are always calculated as a linear distributions. And then we didn't learn yet, but the shear force will be obtained as well. But from here, we're going to calculate the shear stresses. Shear stress, magnitude-wise, not that big, but equilibrium-wise is a very important quantity. Okay. Uh, the Well, there are two types of definitions. One is the statically indeterminate. The other one is a statically determinate. Uh, this is the not just for the beam, but in general, what is a determinate or indeterminate? This concept can be very important in solving any types of structural problems. So statically determinate, sometimes we call SD, statically indeterminate, SI, simply say that the problem can be solved with consideration only statical equilibrium. So that's all you need to know. Statically indeterminate means that when we only consider equilibrium, we can solve all other quantity. And statically indeterminate means that we cannot solve the problem by only considering the equilibrium. We have to consider others. Others means that certain boundary condition and etc. Well, this is the kind of a unclear to you, which is natural. Don't worry too much about it. But I like just to say that statically determinate or statically indeterminate, two different definitions. We will come back again. And what I'm trying to do is just a review briefly what we're going to cover. Now, moment curvature relations. Moment curvature relation. Now here, is the one, say this is a beam, okay? It was a straight like this, and then due to a certain bending moment, and this end, of course, is lift up. At the very the same time, this cross section, which was a vertical, now it rotates and makes angle theta, all with respect to left hand side. So this is the configuration you have to have all the time. Very important geometry view. Again, before deformation, this is nothing new, okay? But I just like to emphasize this was the kind of a beam before deformations. And now, for the convenience, let's assume that on the left-hand side, with respect to a left-hand side, we apply the load. And now this is going to have a deflection, which we're going to obtain, calculated right now, deflection by Vx. So we only pay attention to a neutral axis. This guy will deform like this. And then this neutral axis will deform like that. And the upper surface and bottom surface accordingly deform together. Now, very importantly, this cross-section, original cross-section, remain the plane, okay, remain plane, and also this angle rotation like this. So if this is the rotate this much theta, then we can say this one, okay, this one, we can say theta. While in high school, we learn a lot about the, y equal yx, some deflection curve, say, okay, I will not call y. Say Vx, let's say just the function, okay? Function in terms of x. We have a certain curve like this. Now, any point at x, we can have a tangent. Tangent, what is that? Tangent here, we have a theta, and the slope is always given as the tangent theta is given as the v prime x. This is we already know very well. So that's exactly what I meant. Here we had some line, and then we had a deflection curve like this, and the tangent at here, we can have this. So this is a theta, and the slope, so the slope, the slope is given as the tangent theta, right? Now, just keep that in mind. Let's get back to here. We already have these equations. M equal EI curvature. Again, the K is the radius. This is a radius R, and the K is the 1 over R given here. K equal 1 over R. See, here is a dx. What is a dx? This is the, let's consider this is just the incremental, small dx. Then we can say this is d theta. Now, r times d theta giving us this length, right? R d theta will give us a dx, the length of this neutral axis. Now here, very importantly, assumption is that this is the deform shape and after deformations. But we do know that this one, neutral axis would not stretch or contract. So dx, this one will be the same as before deformations, dx, right? Now, as we just noticed here, the slope at this point is given as the tangent theta is a dv dx. Tangent theta is a v prime or dv dx. Now, this is the assumption we are making, okay? This is the assumption we are making is that small deformation. What does it mean, small deformation? If the deformation is small, tangent theta can be approximately given just a theta. Okay, tangent theta is given as the theta. So tangent theta is a dv dx. So we can simply say theta equal dv dx. I'm gonna just delete other things. So theta is given as a dv dx because we are assuming this theta is small, then tangent theta equals theta, right? Now, the since k is given as a d theta dx, where this comes from? Well, here 1 over r is given as d theta dx. D theta dx. And 1 over r is simply, this is the, this is r. This is a k, okay? This is a k. Now, theta, we got theta in terms of a v, and we simply put it here. Okay, so k curvature or 1 over r is now given as a second derivative of deflections. This is the one we obtain. This is the one we're going to use. Again, where does it come from? It comes from the definition of a radius and also the slope, theta. And combining those two derivatives, we got the curvature is given as a second derivative of curvature. I mean, second derivative of the deflection curve. Okay. So now we obtain moment equal EI curvature or EI 1 over R. Now we see this K as this one. EI second derivative. This is the one we obtain, and now this is there are several equations we have to understand or follow. This is the most important, very simple, but most important the fundamental equation we need to understand, we need to start with in beam theory. So again, moment equal EI second derivative. See, this is the moment curvature relations. I would say moment now is equal EI V second derivative. This is the one we got, moment curvature relations. So again, let me refresh our goal. The Vx, say certain, the Vx, we have a deflection curve, x. Now this V in terms of x is the one, let's say we have a moment distribution. I would say moment can vary along the x, and EI and V double prime is also a function of x. So any point, any cross section, the moment carries is given simply curvature like that. Well, whenever I teach this simple equation, I'm always amazed by how simple it is, but how powerful it will be. You will see how powerful these equations. So we just had a very simple derivation, but keep that in mind. You need to be easily visualize what does it mean. Okay, every point you have here you have a moment, here you have a moment, here sometimes a moment here. Every point the moment will be given as a function of x, and every point the curvature double prime is a relate simply EI. What is EI? EI means that every beam, every point, we have a Young's modulus and then moment of inertia. So moment of inertia and EI has a beam, and then this is a geometric deformation. This is the force it carries. So let's say we have a airplane, well, airplane like this. Now it's a flying, okay? It's a flying, and then a lot of load at the bottom. And now this wing will deflect. Now, as you can see that any cross section along this length, the cross section will have a certain curvature or a certain deflection. If we know the second derivative of that one, we know that the moment at that cross section is we simply multiply EI and V double prime. That will be a moment that cross section carries. Okay, so again, well, sorry, I just repeatedly emphasize is that much important. As you can see, we went through very simple equation. We already know moment equal EI curvature, but only assumption we add is the second, I mean, the slope is a tangent theta, but the deflection is a small, so tangent theta is a simply theta. So theta equal just the slope. Now this slope and this the r d theta dx comes from the definition of radius r, right? This one. Uh, so we combining that 1 over r or curvature is the second derivative. Okay, that's the one we know. So we went through very simple two-step derivation, but now we from here we need to understand as say uh, mechanical engineer. This is a geometry and this is the moment. Okay, we have a other slide will be followed, but we need to fully understand this one. Well, just 1 second. I often like to emphasize or make you feel better with ChatGPT. Uh, I'm certainly a user of ChatGPT, but doesn't need to be ChatGPT. Any AI, you should be able to use it, even in class, of course. Let's say we had a certain. Okay, well, we can just say here. Let's see what they say. Oops. Did I share my screen? I hope so. Okay. Uh, do you see my screen? Yes. I like to, time to time, I communicate with the ChatGPT and then see what it says. We are studying the say deflections uh, due to bending and the well, tell me about it. Let's see what it says. See, it says deflection due to bending refers to a displacement of a structural element like a beam under the action of an external load that causes it to bend. And let's go through these systematically. And concept, when a beam is subject to a bending moment, okay, bending moment caused by transverse load, well, it can be most likely transverse load. What does it mean? We had these types of P and this type of distribution Q, right? So that's why they said the vertical load. This deflection is a small, okay? This is the one small word we need to pay attention. Small compared to the length. Okay, when we say small, we need to be relative dimension. Relative dimension is the length, or precisely, I would say the thickness of a beam. So small means that relative to thickness of a beam is a small. So the small deflection theory of Euler beam applies. Okay, we don't know, we didn't cover this one yet, but the technically speaking, it is often say it's called Euler-Bernoulli equations. Now, the fundamental equation, it says the relation between the bending moment m and the deflection yx, we call vx, but they call yx, is the second derivative is a moment ei. See, this is the one we obtain. I don't want to go next because that's the one we're going to cover, but you can see how it starts. Moment ei. And then we went through so and so on. Now let's ask how do we get the relations between the bending moment and the deflection or curvature. Let's see what it says. Well, it says excellent. That's the heart of beam theory, beam bending theory. See, let's carefully drive the relations again between the bending moment m and the deflection yx step by step from first principle. Now, starting point is that 1 over r, 1 over r, k is given as a 1 over r. Okay, let me do this arrangement like that. 1 over r is a curvature. Now, this is a precise the geometric relations. Curvature in any point. I wonder, I'm sure you learn about the CAD, the a curved line in drawing. And we do have always a curvature. Curvature is a 1 over r. Now the deflection y, this is a full equations. Okay, second derivative. And strictly speaking, there is a 1 over 1 plus and slope scale and 3 over 2. This is a full equation. Now, small slope, we assume that small deformation, small slope, this second derivative, the first derivative can be very much less than 1. That's the assumption of a small deformation. So this term is disappear, and simply 1 over r is the second derivative. See, this is the one we obtain, and here we had a little different path. Tangent theta is a dv dx, and then a small theta is a tangent theta equal theta, and then we got this, and we got that. So as you can see, this result, and this result are same. Mathematically, we neglect this one due to a small deformation. Is the same as here, small deformation, tangent theta equal theta. Okay, so that's the one we have. Okay, next one we will do, but okay, actually the moment curvature relations, we already have epsilon equal y prime, y well, it's a little bit confusing. They should not say y prime. derivative. Well, this guy makes mistake sometimes. Well, I said I don't like the y prime, and he just changed it to a z. Man, I don't like the z. So this is the one. Double prime. Oh man. Uh, the heck is okay. So this is the one. If strain is z over r, that what is that? That's the what we learned last, the chapter, and that is the this guy, the most important drawing. The see here, see here, the epsilon x equal uh, y curvature. K is the 1 over R, right? 1 over R. So they are using the Z. So that is the Y. Y is the again the vertical coordinate and proportional to 1 over R. 1 over R is that d theta dx. So this is the one we already covered last week. And that is the called stress, I mean strain stress across the depths. This is the fundamental geometric deformation. Now the stress strain, it says the sigma equal Young's modulus times epsilon. That's the what we got. Now, as you can see, next step will be combining this one, put these things into here. And see, last week, the definition of a moment is the simply sigma xx, and this is a force, and then will cause the moment by applications of a y, and then integration. And this will have a strain, and strain will have a and y and this there and dx, and then integration. So that's exactly what it does, what they do here, and the second derivative here. This is the what we learned last semester. I mean the last chapter. Uh, and now here, second derivative. Uh, okay. Again, this equilibrium. That's what I meant. Equilibrium was studied last week. And then 1 over r is now given as a second derivative. That's what we learned today. Okay, that's what we learned today. Simply like that. So we have a moment equal EI double curvature. So the second derivative is given as a moment divided by EI. Okay. So we will do a next step, but as you can see, what is the fundamental equation? The fundamental equation is the one we studied last chapter, is that EI, this one, and then today we learn 1 over R is given as the second derivative. 1 over R is the curvature, okay? So this one and that. And then we will do a next step. Let's get back to our slide. So what I'm trying to share with you is the equation or concept you are following is not the I mean it's very common derivations and procedure in beam theory. As you just saw that, even ChatGPT would follow the exactly same procedures. Okay, what will be the next one? Next one is the equilibrium. Okay, equilibrium. Equilibrium is the force equilibrium for beam. We can have two types of equilibrium. See, when you have a beam like this, uh, the uh, the force causing the beam, causing the deflection is the mainly vertical load. Okay, let's consider moment later, only vertical load. Let's say this is a beam, and we have a certain vertical load like that. This is the beam, and which needs to be equilibrium, of course. Okay. Uh, let's say we have a certain boundary condition here, or boundary condition like that. And then we always have a y-directional force. This. What else? Y-directional force. We have a force, reaction force given here and given here. We don't know the reaction force, but whatever the reaction force will be or should be calculate with considerations of equilibrium. So either this equation or that boundary condition, whatever boundary condition, we will have a reaction force, okay, reaction force, depending on the boundary condition. So this reaction force has to be in equilibrium with this external load. So y-directional equilibrium and the moment equilibrium. Moment equilibrium is what it means. Well, simply say, let's say we have a certain load and certain load and certain load here, and this would not rotate. Moment z, so z moment should be equilibrium, and y-directional force equilibrium. That's the one we this beam have to meet two force equilibrium equations. This is obvious. No matter what the structures are, they have to be in force equilibrium. Of course, we can consider Fx equals 0, Fy equals 0, and moment equals 0. This is the typical moment, the force equilibrium in two-dimensional plane. Now X, since we don't we don't consider any X forces, we don't need to consider. This is automatically met, so we don't consider that. But y-directional and the moment, that's the one we have to consider in calculations or in beam theory. Okay, so this is the force and moment equilibrium equations. Okay, we are more slight about the equilibrium equations. Okay, just pay attention to what we meant, what we can do with the equilibrium. Say we have a certain, we call it, this is a clamp boundary condition, and we have a beam. This is kind of a typical condition for the wing, airplane wing, have a long extended the beam type, and with the length L, and then subject to a load, can be any load, but let's say at the tip, we have a vertical load P as a simple case. Now, obviously, these structures as it is in equilibrium, no. We need to have a kind of a reaction force, V, and reaction moment m here to make these structures in equilibrium. Actually, these two reactions makes the structure in equilibrium. That's the one occur at this boundary as a reactions. So there could be there should be some vertical load V and the reaction moment M, which are unknown. We don't know yet. But how much the force, how much moment should occur there? How do we calculate? Well, these guys generate to meet equilibrium. What kind? Well, y-directional equilibrium and the moment equilibrium. So y-directional equilibrium, we have a P and we have a V here. Well, certainly moment is not the y-directional force. And so V minus P equal 0. That's the for y equilibrium. And another one is the moment equilibrium. Moment equilibrium. Well, moment, we always need a point which we need to consider moment with respect to a certain point. So moment at say here we consider a moment at 0. The moment equilibrium, we can consider any point. We simply consider here the moment over here. Okay, so moment at here, this P would cause a moment. See, moment is always plus like that. So with respect to here, this P would generate this much load, negative direction. So that's P times L. And there is a M0. Let's call M0 as indications of a reaction. So M0, let's say we have a positive M0, which is unknown. So at this point, we have this one, and P times L will cause a moment as a minus. This is the moment equilibrium. So simply, we can obtain the V and moment 0 like that. This is the reaction force which would generate at this point. So with this simple clamped beam, if we apply the P, the reaction force will be the P, and the reaction moment will be a P times L. Okay. What I'm doing here in this slide is to demonstrate what kind of a concept, what we can do with this condition, force and moment equilibrium. Okay, force and moment equilibrium. So any beam, actually, let's get back to a problem statement here. Any beam under the Q distributed load and the concentrated load or concentrated moment, we do have a certain boundary condition. This guy, external load, may not be an equilibrium. Then one makes this structure to be in equilibrium while this boundary condition. We may have a certain boundary condition. We can have a simple support, we can have a clamp, or sometimes we can have a free. So clamped, oh man, this is so important. Clamped and the simply support and the free boundary condition. Don't worry, we will cover this one again. So we have three types of a boundary condition: clamped, okay, and simply support, and the free boundary condition. So whatever boundary condition we have, at this boundary condition, we would have a certain reaction force. Reaction force would make this structure in equilibrium. Okay, that's what reaction force does. Okay, so that is the point here. No matter what forces we apply, no matter what boundary condition we have, we always have to have equilibrium. Okay, so uh, see, this is the one we have a, relation moment and the double derivative, and these two force equilibrium, y and moment. Okay, now next one. What is this? This is the internal forces. Let's just skip a little bit because this is the not the mainstream, but internal forces are of course the important. Okay, well, let's get back here. It is 2 o'clock. Let's have a 10 minutes break and then let's come back. Okay, the 10-minute break. So it's like a beam theory. While the sorry to use the some mathematical derivation and procedures. I know it's kind of a boring, but we do need to understand the mathematics. That is the unavoidable. So we have to go through. but not many times. This is just the few critical equations, moment and curvature and deflection. Those are two equations. And then force equilibrium. Those are three equations. Now we will have a final form. The basically what will be given is the external load. What we want to obtain is the deflection curve. Okay, they're simply like that. And once we know that deflection curve, we can do many things. We can do design, and we can do optimize the design, and we as a mechanical engineer, this is the key, uh, the uh, the point industry expect from us. Let's say you work on the design of a certain wing, airplane or automotive, or even say the humanoid, any structures you design, then this fundamental understanding of a beam is the critical. Well, speaking about humanoid, let's say this topic is become very interesting and very beneficial to our, the society. So we mechanical engineer need to understand the what types of humanoid will be available. You are the one, guys, will get used to it. And then not just as a user, but also a designer. How can we design the humanoid structurally, electronically, or through AI? This is the topic we should be able to answer. Uh, just for the purpose of, mm, man, I have some trouble with this Zoom. They keep changing the. Okay, I just want, before we continue, I'd like to make sure that all here. Uh, let's see. Well, show yourself. So we have 18 participant student. Okay. 구현호, I cannot see you well, but anyhow, I like to see you, sometimes face to face. But anyhow, uh, I just want to make the one comment. I mean, which I already made early uh, class. The online class like this can be very useful and effective. But only concern is that the student can easily lose attention. So all you need to is just keep paying attention. then we can do a lot. We can share the older screens and the Excel and the internet and ChatGPT and our class. So very effective, and time-wise is also effective, but we easily get distracted. That's what I like you to pay attention to a class. Uh, I hope that you should get more used to these types of online for you to be a good, you know, real professional engineers. So, well, before continue our class, let's get back to the sometimes it's difficult to confirm my screen is well shared or not. Okay. Um, okay, let's get back to here. Okay, so the before we move further, we like to get a simpler, say, uh, design case so that we can better understand why we need a beam theory or deflections. Uh, let's say we have a simple beam with okay, uh, what the hell? What? See what it says. See, we engineer before we learn to learn some, the subject, which is of course is not new to, is new to us. The We need to understand why we need to learn this subject. Well, it says great idea. Let's use a very simple design case to see why beam deflection, not just its strength, matters. Man makes it more complicated. Uh, See, for example, we have certain structures, okay, happen to be a beam. And we as an engineer, we designer, we like to see how much deform and how much stress we have. I don't want to show some equations. I want to uh, show some cases. Let me Okay. Let me let me just define a simple case. Okay. Say we have any types of beam, and let's say we have this beam is laid on the two support. Do you have a pen? Everybody should have a pen, right? Uh, right, this pen. And then just simply support like this. Okay, hold like that. And then you apply the load at the center, and then try to feel that where this pen can break. How can we break the pen, and how much force you need to have? See, this much load you apply. Can you predict how much load it can support? Um, well, this is a very simple case, like this, okay? And this beam is certainly have diameter and the Young's modulus and mathematically bending rigidity. So now we like to know when and how much the vertical load it can carry without any, the failure. See, this is the one. Uh, and this one is a beam, but we can consider as any pen structures or even larger. It doesn't matter, airplane or anything. Just try to help you visualize. And this is the force P. And this one, I'll just say EI. Well, EI is can be a little bit unclear, but this can be some cross-sectional property and Young's modulus. It can be a steel or plastic, anything, or it can be the I-beam, which we covered in the homework, or it can be a circular, or it can be any types of rectangular cross sections. And the Young's modulus can be a steel or aluminum or certain plastic. You can easily get the certain property. So EI is a given. Okay, EI is a given. And now the point is that when and will this beam break? Means that when means that how much load P can be carried, and this is the length L. Now you tell me your feeling when where the beam will break. Huh? Can you tell me where this beam will break under this load? Here or somewhere here or somewhere here? How do you feel when you push this one? Well, I'm sure that you would feel that the pen will break at the center, right? Anybody disagree? I'm sure you feel the same way. The pen will break here. Now, how and why you had that feeling? Why you feel that the pen will break here? Well, you just feel that from experience, right? Well, this is a simple pen. You can easily say, "Oh, this is the weakest point." But imagine this can be complicated structures like the airplane or the automotive or even bike or humanoid. It's not easy to say. So we need to have a little bit of a systematic and precise derivation. That's one point. Now, let's say we know this is the P, then again, when will this break, and how much the P can break? That's what we let's say like to know. Okay. Well, this is a very simple. Even though we didn't learn much, this is a not that difficult. And also, another interest is that how much this beam will deform. How much beam this will deform means that how much this can you bend? This much. This is the deflections. Okay, this is a deflection. How much? I would say the V, because we use the V. How much it can bend? Hmm? Well, if you have a pen, well, it's not that easy to break, but the deflection will be very small. But you feel something bending. You feel something deform. That is a very small amount. But imagine, can you break? Anybody can break? Certainly you can break, but when it break, the deflection is not that much, very small amount, just a few millimeter. This pen will break, right? See, such a small deflection V, this pen can break, and then as we assume, the deflection can be small, but such a small deformation may lead this structure will break or fail. So how important it is to able to Vx, this is the V, I mean the X, and then this is a V. So this is X function, but simple to say how much will be the deflection delta means that if this is the half at the center, this is the delta, how much it will be under P. That's the one we like to able to predict, able to calculate. When this pen break, how much maximum, I would say maximum, this pen can carry. And also, break means that how can we, uh, uh, now let's try to answer these two questions. Very simple question, but you can see that, this simple one help us what we should be able to do. First, as we discussed, by the way, this is not the new theory. This is just the sample uh, case so that we better understand why we study this subject. Okay. So when we apply the P here, as we know, there can be a certain reaction force. Why? Because this beam without support, this won't be equilibrium, right? Force equilibrium. So, well, we can use a several step, but simply you can easily say P over half of the P can be supported at each end because this is the same length, L over 2 and L over 2, right? So with this one, this will be, I would say, uh, equilibrium. Equilibrium means that Y equilibrium and moment equilibrium. Now, very importantly, the moment x, we need to know. Let's say we know the pen will break at this point. Then how much the moment over here? How much moment here? Moment is that say here this much, and then p over 2. The moment here will be, we just cut in half and then see how much load needs to be there to make this structure in equilibrium. Say this moment is that this is a half of 2. The moment is the p over 2 times L over 2. So simply p over 2 times L over 2 makes the PL over 4. This is the one. This is a moment you should carry at the center, right? Now, let's move for further. Now we know that here moment carry is the P over L over 4. We just look at on the left-hand side. We can certainly consider on the right-hand side, the result will be the same because of it's symmetric. So anyhow, the moment is here. Now, back to the subject we learn how to calculate the bending stress is that remember the sigma equal force divided by the cross section times y. We learned that. We already know that. This means that graphically we are saying this much. This is a linear distribution, and then this would give us how this sigma x, this is the x, sigma x can vary. At the bottom, maximum. What does it mean? Tension. At the top, we have a compression, maximum. Right? Now, to get this maximum tension, this will be, we need to multiply the y. This is the h over 2 with the cross section height, let's say h. So from the centroid, our neutral axis to a bottom, distance will be half of the h. So this will be m over I times half. Now this is a minus, so minus minus plus. This is the maximum stress occur here, right? So this is the maximum stress occurs here. Now back to our simple engineering prediction. This will break, the beam will break on the P, and here more precisely, okay, more precisely, this guy, this maximum is the maximum stress will reach when this beam will break. This sigma x reach this yield strength. You know the yield strength. Yield strength is the one the material will yield or break or fails. So this is the maximum, and this is when we reach the material property of a strength, this will fail or break. Oops. Oh yeah. And now here, moment from the equilibrium, we learn this one, so we can put it here. So P times L over 4 times, I'm divided by I to H will be, now what is I? Well, we We can consider circular, we can consider rectangular, it doesn't matter. Well, to make it simple, easy to remember, well, let's consider this pen. That's okay. So as you can see, depending on the cross-sectional shape, the pen with the circular cross-sections or rectangular or inside the empty, inside the field, doesn't matter. Say this is the pen, okay? This is a pen. Say inside DI and outside DO. This is the, let's say, plastic, okay? Plastic. Then what would be the Young's modulus of a plastic? Well, there can be many, many plastic, but let's say, I don't know, I have no idea about this material, but the PVC, well, that is a very common material, PVC, and then we can get the Young's model. What is the D0 and DI? D0, well, I would say 10 millimeter. DI, I don't know exactly. I need to, man, I cannot open it. But let's say 8 millimeter. So that the thickness can be 1 millimeter. See, this is the geometry, and this is the Young's modulus. And from here, what do we get? We get the I. Oh, where is the E? There's no E there. We don't need to consider E, Young's modulus E. It's strange, but let's say equation says we don't need a E. Means that if this is the a plastic or steel, the stress will be the same. A little bit difficult to understand, but equation says there is no Young's modulus. It's fine. Let's buy that. But I is the, kind of like that, and we need to know what is I. What is the say bending or moment of inertia of a circular beam with a D0 equal 10 millimeter and DI equal 8 millimeter. Okay, what is the moment? Let's call more clearly, say bending moment. Well, we can simply calculate and the let's see. See, this is the moment of inertia. We can drive that. We can drive by definition of a bending result, but we always can refer to or ask AI. This is the one, D04 and and the DI4 and etc. Say D0 is given as a 10 millimeter, DI given as this 8 millimeter, giving us this, and finally I is the 2.9, 10 to the, 290 millimeter 4, okay? 290. The unit is important, of course, millimeter. So let's get back to here. The I is the 290 millimeter 4 times. Okay, 4 of this circular. Now, what else do you need to have? Well, the H. What is the H? H will be at the bottom, meaning that uh, the H will be D0 divided by this will be a 5 millimeter. So we do know I, we know the H, and now L. L, how much the L will be? Well, this one I would say uh two hundred millimeter. Okay, so 200 millimeter. And now, very importantly, this would be will be see, sigma yield. What is a sigma yield? Huh? Sigma yield. Now here, the stress will be independent of a material, but there will be a what is the yield strength? Yield strength, see here, well, it gives us a Young's modulus 2.3, 2.5 and 3.5 gigapascal, and the tensile yield strength, ultimate and yield, well, there are several terms, tensile yield and ultimate, well, we'll get back to here, but the design the yield strength will be a 50, I will take this one, 50 megapascal. Okay, so this guy will be 50 megapascal. Well, a little complicated, but here, very importantly, we like to know how much the P should be, and we just calculate the I, and we got the L, we got the H, and now we got this one, 50 megapascal. So let's calculate the P. Sorry, a little bit. Sigma Y, okay, and the times 8 divided by L and divide by H and multiply I. Hmm? Okay. Okay, this is the one we got so far. Again, the objective is that we like to calculate the P max. P, say here, P equal sigma Y, well, I don't need to rewrite here. Sigma Y, what is that sigma Y? 50 megapascal, okay? 50 megapascal times 8 times, what is L? L is the, what was L? 20, oh, sorry, 200 millimeter. Okay, this is a millimeter. And what was H? H was the half of the pen. So that will be a, blah, blah, blah. H will be 10 millimeter, right? Anything? Oh, and what is I? I is a 290 millimeter horsepower. And now megapascal, don't get confused. Megapascal is what? 10 to the 6 Newton per cross section millimeter scale. Everything is okay. See, double check the unit, millimeter scale and millimeter. So this and that. Only Newton are left. So we are in the right. No, this is the millimeter, and this is a 10 to the 6. So we can say 10 to the 6 will be this up here. Then Newton per millimeter, because a meter is the 1000 millimeter. Okay, this is okay. So 50 divided by 200 times 10 times 290. So anybody can calculate, say about, huh? About 5 times, about five 500, something like that. No, sorry. Okay, five. So just 5.5. Is that okay? Or no, about six or 6 point something. Anybody tell me? Hmm. Uh, I'm sorry, there was an 8 there. 8 is missing here. Okay, 8 comes from the yeah, 8 comes from here. Is it about 5 Newton? I mean 50 Newton? Well, let's calculate. Oops, oops, sorry. Is that okay? So, okay, result will be according to our simple equations, we got 58. Okay, 58 Newton. 58 Newton means that about the 6 kilo. So to break this pen, how much force you need to apply? You need to apply the 6 kilo. 6 kilo, this pen will break. Well, anybody can want to demonstrate? Please, welcome to do that. Now, let's ask the what it says. A I would say the pen of PVC subject subjected by the a concentrate load at the center, and the okay, the length of the beam on the pen is 200 millimeter, and OD equal 10 millimeter, and the ID will be 8 millimeter. The pen is supported by the supported at each end. Well, we should say a simple support. Anything is missing? Importantly, PVC and pen and OD and ID and length, everything is given. Now, what would be the maximum load can the pen carry? Well, without any material failure. See, this is the what we went through some beam theory and the reaction force and cross section. This is very difficult procedures, by the way. The length L and this, well, you give us all the information, so we went through, and this, okay, it says 58 Newton, exactly same as the we got, 58 Newton, about the 5.9 kiloforce. The shear is negligible, well, which we also neglected, and deflection at this point. Deflection, okay. Now, deflections, what does it mean? See here, the pen, we don't know how much this deflection will be. Delta. See delta here, we don't know. That's the one we like to learn. How much it deform when it break. See, if we know the delta, we should be able to say, oh, this pen will break. Or if this is any structure or airplane, we can say how much it can deform without failure. So we don't know yet how to calculate the delta. That's the one we like to do. And the ChatGPT, this guy, we already like to say. So how much it deform? The deflection at this load will be large for PVC on the order of 11 millimeter at midspan. See, when we apply the load here, and if you apply the 5.8 kilo, then it deflects like the 11 millimeter, which is a lot, by the way. Then it fails. So again, deflections, we pay attention to the stress, but the deflection is also very important because if we know the deflection and the stress is linked together. Okay, linked together. Um, Let me get back to the our favorite 3+1 flow chart. See, this one, we just, let's compare what we have done. This is the force. In our case, again, I'll redraw here. We have a certain condition here, and we have a P, and we like to know how much the P load. See, here, the force will be P, of course. Material will be a PVC, and deformation. Now here, deformation is the one we like to have. This is a delta. Well, delta or the deflection as a function of x will be more ideal. If we know the deflection curve would be nice. We can imagine this would deform like this, right? And that this is a maximum delta. So deformation condition. So we have some step, and this is the three step will be the outer external condition. Force P, PVC beam is given, and deformation is now we like to know because we can observe the outside. And equilibrium, what is the equilibrium here? Equilibrium, this beam needs to be equilibrium, meaning that how much the reaction force. So equilibrium is that I would like to draw free body diagram, P or something. Okay, this is the equilibrium, and let's say this is a V, this is a P. Okay, I'm sorry, I will call, okay, V0, V0. We already easily know the V will 0 will be a P over help. So anyhow, equilibrium and deformation condition. What is the deformation condition here? Deformation. While V at X equal V at L, what do we have? This has to be 0 because we are simple supported. See, we support it here, and then we deflect. So at the end, at the both end, no deflection, only a central load will deform. And see, strain, see, we already know Y over R or something. And stiffness, we already, this is a PVC, order of 3 gigapascal. And the strength, importantly, how much was the strength it can carry? It says, man, how much was it? It's what megapascal? I forgot the 50. Was it 50? The PVC strength, well, let's get back to here. I will put these things here. So the strength will be, okay, 50 megapascal. This is the strength. This is the strength it can carry. And so strength, as you see here, strength yield will be a 50 megapascal. So sigma x, we obtain, how much was that? Sigma x will be moment divided by I times y. So this sigma x should be less than sigma y. And then, the stiffness usually given E and the strain is like this. So my point is that even this 3+1 flow chart can apply to this simple case where the beam or pan supported with two ends and subject to a central load of P. And then we should be able to get the P, which can cause pan fail. At the same time, now we can get the deflection curve. How much? It says which we are learning now, we are studying now, but we don't know yet. The deflection will be 11 millimeters. So deflection will be 11 millimeters. 11 millimeter. Uh, so it can deform like this, 11 millimeter. See, this is the flow chart or 3+1 flow chart for our beam case. As I said, this 3+1 flow chart will apply to any case, even derivation of a cross-section, a beam theory, or a simple bar, or beam, any case. Now here, this we can double check this 3+1 applied to a beam under the load and see this. So again, what we like to know is the this guy delta equal Vx. How can we get the Vx? And importantly, we consider the equilibrium. Equilibrium. We consider the strengths. Well, this is the only for the design. Okay, so I just like to remind ourselves of what we do. Now let's get back to let's continue. So basically, we like to do is that rather than considering equilibrium, rather than considering this strain and deflection, well, what if we combine everything? Well, just to combine everything, we hope to have a one governing equation. So simply apply P, we get the delta. And then internally, we get all the stresses, stress, and things like that. See, moment here, moment is what? EIV double prime. So if we know the Vx as a function of x, we can immediately get the moment, and we get the sigma, and then we get the maximum allowable P. This is a very important point. 오케이. 한국말 다시 할게요. 자, 지금 어떤 빔에 어떤 물성치가 주어지고 길이가 주어지고 하중이 주어졌습니다. 우리가 바깥쪽에서 처짐을 관찰할 수가 있어요. 그래서 우리가 직접적으로 하고 싶은 거는 이 빔에 하중 주어지고 빔이 어떤 재료고 처짐을 구할 수 있으면은 안쪽에서 스트레인 구할 수 있습니다. 왜냐? 1 over R이 뭐예요? 우리가 지금 어떻게 봤어요? V의 더블 프라임이라는 거 배웠죠. 그 다음에 시그마 X, 여기 모멘트가 V의 역시 더블 프라임이라 그랬죠. 그래서 여기다 집어넣으면 시그마도 구해지고, 시그마가 재료가 뭐 PVC다, 그러니까 50 메가파스칼이라면 그거랑 작은지 큰지, 그러니까 이퀄리브리움을 따로 고민할 필요도 없고, 이거를 따로 고민할 필요도 없고, 이것만 안다면은 이 VX 지금 뭐 원하는 게 뭐냐? P를 주어지고 VX만 알면은 모든 게 구해집니다. 다시계에서 미분을 할 수도 있고 하기 때문에 that's the object. 우리가 그게 지금 하고자 하는 겁니다. 그래서 이 지배방정식을 이 지배방정식 안에 부를게요. 지배방정식이 뭐냐? 지배방정식이 이거가 주어지면은 이거가 있고 이것이 주어지면은 그냥 이 그 VX를 구하고 싶어요. 그게 지금 우리의 바람이에요. 그런데 여기 안에는 뭐가 있어야 될까요? 우리가 폴스 이퀄리브리움도 고려해야 되죠. 물성치도 고려해야 되죠. 그 안에 스트레인의 변형도 고려가 돼야 된다. 그 얘기예요. 자, 세 개 얘기할게요. 평형도 고려돼야 되고요. 그 다음에 물성치가 고려돼야 되고요. 그 다음에 그 안에 스트레인하고 디스플레이스먼트, 바로 변형이 어떻게 돼야 된다는 걸 세 개가 다 고려돼서 뭐가 나온다? one governing equation이 나와서 이거를 구하고 싶다라는 얘기예요. 그래서 되도록이면 내가 수학, 그러니까 그 심볼을 쓰고 싶지 않지만은 뭔가 우리가 구하고자 하는 게 가버니케이션. 가버니케이션이라는 것도 수학적인 얘기지만은 뭔가 하중이 P가 주어졌어요. 뭐, 나중에 배웠지만 어떤 수직 분포라도 좋아요. 그 다음에 뭐를 구하고 싶어요? VX를 구하고 싶어요. VX가 구해지면 어떻게 된다 그랬어요? 그러면은 V의 더블 프라임을 구할 수가 있고, 더블 프라임을 구할 수 있으면, 스트레스를 구할 수가 있고, 왜냐하면 모멘트가 뭐예요? EI의 더블 프라임이니까, 시그마는, 모멘트에다가, I에다가, Y니까 금방 나오죠. 그러니까 모든 게 다 구해줄 수가 있어요. 그래서, 물성치, 처진 곡선, 그 다음에 이퀄리브리움이 뭐였어요, 우리가? 모든 y가 0, 모든 모멘트 이퀄 0이라는 이퀄리브리움, 물성치, 이것이 다 합쳐져서 우리가 가버니케이션이다라고, 어, 그러니까 이것이 다 합쳐서 let's drive the carbonication so that once we solve this one with the input this we would have a Vx as a function of x then everything uh, every condition will be taken care of automatically equilibrium, material property, and then strain deflection equations. So this is the one we like to obtain. So remember, we have to consider equilibrium and these moment curvature equations, and that is what the carbonic equation is. So that's why next subject is the carbonic differential equation. This carbonic equation will be happen to be differential equations. Carbonic differential equation for beam. 이게 그래서 이제 이 서브젝트가 나오는 겁니다. 다시 한번 리마인드 하는 거예요. 자, 이게 in general we have a function of x, the force, okay, the force, vertical force. We consider the vertical concentrate load, but in general the load can be given as a qx. Free body diagram means that let's say we got the any the uh, length dx. So on the left hand side would have a moment. On the right hand side would also have a moment. V here and a moment here, and beam. Always we need to have a shear force, shear resultant. So, by the way, beam cross section, we always have a moment and the beam and the shear force. So shear force here is a Vx, and shear force after dx, Vx will have an increment dv. Moment at the left hand side, moment x will have an increment. How much? We don't know yet, but a certain increment. So this is the kind of a free body diagram. Any beam, we just took this small portion and then we consider. Within this region, we would have a QX. We may not have that, but in general, we have a QX on the left-hand side, the moment and shear force. On the right-hand side, the moment increment and shear force increment. This is the incremental portion of the beam, and then all the forces will be applied. Okay. So what we are trying to do is to get a equilibrium equation. Okay, equilibrium equation. I'm sorry for my bad handwriting, but this is what we like to do. So here, this is the one on the left hand side, the Vx, and on the right hand side, the Vx, and moment and moment. Some of you, or most of you might have some difficult time. 교수님, 왜 이건 화살표가 내려가고, 이건 왜 화살표가 올라갔다가, 왜 이건 이리 갔다가, 이리 갔다, 이렇게 하는가라고, 좀 세밀한 사람들에게 하는데, 너무 신경 쓰지 마세요. 일단은, 충분한 이유가 있는데, 너무 그 distract 당하지 마시고, while just trust me, there will be a certain moment and this. Now, simply say this is a left hand a negative, so this has to be negative. And positive and positive and negative and negative and positive and positive. The simple reason is that this guy, okay, just a cross section, this will be a reaction force like that. So anyhow, if we consider y-directional force equilibrium, on the left we have a minus Vx, on the right Vx plus dv, and then Qx dx. Well, this is the distributional force, so we multiply the dx. Okay, this is the old y-directional force. They have to be in zero, I mean equilibrium. So we have a zero. Now let's consider moment equilibrium of this small portion. Moment on the left-hand side. Okay, this is the negative minus. And now here, Qx dx is a force multiplied by the 2 point, because if we consider moment here, this guy will be acting as a force by multiplying dx, and then multiply by the distance to get the moment, I mean the force, I'm sorry, moment. And then this is the force and dx, and this is a positive on the here. So this is the all the force has to be zero. This is all the moment have to be zero. Well, to this one will disappear and this, and then giving us a very simple but very powerful equation, dv dx equal minus qx. Now moment, to make long story short, we got the moment dm dx equal minus vx. Okay, this is the two equations we got from equilibrium equations. Here is the v derivative. Here is a v. Let's get rid of that v. Okay, v. Simply we put it here. Moment derivative, twice of derivative will be qx. Can you visualize that? Moment, second derivative, will be the qx. What is this? This is the equilibrium. Now, this is the another fundamental equations we derived in beam theory. Second derivative of moment will be a qx. Okay, this is the equilibrium. So back to here, equilibrium in terms of a v, we got moment equal. I'm sorry. The moment second will be what? V shear force. What am I doing? Okay. I will write here dv dx equal q, and the m dx equal v. So here now we have a moment. Second derivative will be a qx. See, q is the here external force, and the moment is here. If we consider this one, we don't have to consider equilibrium. This is the equilibrium, and this is the one. See now, as you can see, here is the one, and here is the one. So just the I know it's not it is very new to you, but the moment distribution, moment variation. Let's say we have a beam, any beam like that, and you have a Q distribute load, and then the moment, every point moment, second derivative of a moment will be the Q at given at that point. That is the uh, equation we got from equilibrium. So uh, I don't want to repeat this one. So this is the equilibrium. Now this is the final. Okay, pay attention. To make a long story short, this is the final. Beam equilibrium. It says moment second derivative will be Q. And now we already have a moment curvature equation. Moment equal EI, second derivative of V. Let's say we put these things into here. What do we get? We get 4 times derivative over V, because this is a second derivative. We have another derivative here. So we have a 4 times the derivative of EI will be a Q. Oh man, so this is a final. Okay, this is a final. And now this can be, if you want to get the deflection, this is the one you can solve. 지금 이 바로 전에 Q가 주어지고, 우리가 그냥 간단히 처짐 V를 구하고자 했습니다. 어떻게? 바로 이 이퀘이션만 이제 솔빙하면은 이퀄리브리엄, 모멘트, 그 모든 스트레스 스트레인 릴레이션이 다 고려할 필요 없이 이거 하나만 풀면 된다라는 얘기입니다. So this is the final equations as a governing equations. 그 여러분들 뭐 2학년 이상이니까 뭐 가버니케이션, 그다음에 PDE, 뭐 이렇게 미분 방정식, 디퍼런셜이케이션, 이런 것들은 알 거라고 보는데, 실제 어떻게 사용하는가는 사실 좀 많이 익숙하지 않을 수도 있는데, 지금 항상 디퍼런셜이케이션을 풀 때는 뭐가 필요해요? 경계 조건이 필요하죠. 네? 경계 조건이. 그래서 이것이 4차 미분 방향, 그냥 수학적으로 봤을 때 이 4차 미분을 풀기 위해서 경계 조건이 필요하고, 몇 개의 경계 조건이 필요하겠어요? 이거 인테그레이션 하면은 적분상수가 몇 개 나올 것 같아요? 4차니까 하나, 둘, 셋, 네 개 나오겠죠. 그래서 그 네 개의 컨스탄트가 어디서 나와야 될 것 같아요? 바로 경계 조건. 몇 개 경계 조건? 네 개. 적분상수가 네 개 있을 거니까. 여러분들 수학을 잘하니까 수학적으로 얘기하면 좀 더 이해가 쉬울 수 있는데, 자, this is a final differential equation. Fourth order derivative is given as a Q to get the V. Now, since this is a 4 times of derivative, how many boundary conditions do we need? 4 times, four of them. 그러면 이제 모든 게 풀릴 수가 있다라는 얘기입니다. 얘기예요. 자, 여기서 우리가 아까 했던 very simple한 빈 문제로, 우리 펜 문제로 다시 한번 돌아갑시다. 여기 아까 우리가 P라고 했었죠. 여기 아까 뭐 했어요? 뭐 simple support라 그랬죠. simple support라 그랬어요. 자, 여기서 P를 가해서 우리가 뭐를 구하고자 했습니까? 우리가 뭐 시그마 맥시멈도 구하고 P 맥시멈 이게 언제 브레이크 할 거냐? 그다음에 또 VX도 구하고 싶은 거였어요. P가 주어졌을 때. 주어진 건 당연히 영스 모델려서 주어지고 그다음에 D0 주어지고 DI가 주어졌어요. 그리고 지금 우리가 보니까 이 아이가 어, 이 아이의 V의 하나, 둘, 셋, 넷 이퀄 뭐였어요? 우리가 지금 유도한 게 QX였어요. 이게 지금 우리가 이제 지배방정식으로 구한 겁니다. 이것만 풀면 모든 게 된다 그랬어요. 왜냐하면 3, 5, 1에서 중간에 있는 5가 모든 게 다 합쳐져서 이걸로 하나로 나온 겁니다. 그래서 E는 주어져 있고 I도 주어져 있고 구하고자 싶은 거 V is the one we like to obtain and from the given Q. Q is the distributed load. But as you can see that how many well the constant integration. 인테그레이션 이거 V 더블 네 개 어떻게 해야 돼? 네 번 적분하면 되죠. Right? You just simply integrate the four times you will get the V. 그래서 we will need a, how many boundary condition? We need a four boundary condition. 그래서 at x equal zero, x equal zero에서 이게 이렇게 simple support. 그러니까 여러분들이 이게 just the support by your finger. What do you support? At x equal zero, v equal zero. That is the known. And also, here we don't apply any moment. We don't, these may have some deflection slope. We don't know. We have a slope. We don't know. But we know is that moment equals zero. 근데 모멘트는 또 뭐예요? 이하의 v 프라임이니까 이것이 제로면은 so double prime equals zero and x equal L 여기서도 마찬가지로 L에서 deflection is zero and the moment equals zero. In other words, the double curvature equals zero. 자, 그래서 carbonication, we know now this carbonication, and now we do know this four boundary condition. So we should be able to get Vx. VX만 알면은 다시 얘기하지만은 모든 게 풀려요. 어떻게? 모멘트 어떻게 구합니까? 그냥 EI에다가 V에다가 두 번 미분만 해주면 돼요. 그러면은 모든 모멘트의 분포가 나옵니다. 그리고 시그마 X는 어떻게 구하면 돼요? 시그마 X는 모멘트에다가 I로 나누고 Y로 곱해주면 시그마 X가 나와요. Right? So again, once we have the moment, I mean, V deflection, you will get the moment, you will get the stress, and you know the strengths or yield strengths, everything uh, can be solvable. You can design. 자, 이게 프로시저인데, 여기서 하나, 임포트한 게 뭘 것 같아요? 다 풀 수 있을 것 같은데, 여기는 QX인데요. 여기는 P고, 이걸 어떻게 해야 돼요? Right? This is a QX, this is a P. 그래서 요 P가 QX로 어떻게 표현하는가는 알아야 되겠어요. Now we have to know how to express this concentrate P is given as a QX. QX is a distributed load. This is a concentrated load, and this is the distributed load. 이것만 하면은 모든 게 이제 다 풀린다라는 것입니다. 오케이. 요 과정이 이게, 뭐, 심플한 것 같지만 약간의 매스매틱이 필요합니다. Why? Because the QX is a distributed load. P is the concentrated load. 여러분 혹시 델타 펑션이라고 들어봤어요? 이게 지금 차원이 다른데 델타 펑션. 이거를 조금 더 요렇게 얘기할 수도 있어요. 요렇게. 이것이 분포하중 QX인데, 여기가 이제 좀 집중하중은 우리가 QX가 분포하중이 났으니까 힘들고 QX를 펑션으로 이렇게 표현하자. 이렇게. 뭐 여기가 지금 한 포인트, rather than just one point, we consider a little bit of a finite width, but the point is that this B and this is Q0. Uh, so this width times Q0 will be a P, right? This is a P. So this way, okay, this pattern with a width of W and the height will be Q0, and this times will be a concentrated load. And now this P can be expressed as a QX. Well, a little bit complicated, the 0, 0, 0, and then suddenly Q0, and suddenly down and 0, 0. Well, this is a mathematics. We don't need to worry. So, but 이게 지금 Q0고요. 여기가 아까 W라고 했는데, 이것이 점점점 W가 0으로 가면은 이게 만약에 반으로 줄면은 뭐 이렇게 되겠죠. 예. 그래서 점점 가면은 이게 집중하중이 된다. 그 얘기입니다. 그럼 왜 이렇게 복잡하게 생각을 하느냐? Well, simply because we consider all load as a distributed load. This is a distributed load. This is a concentrated load. 지금 이런 펑션 여러분 기억나는 거 있어요? 바로 델타 펑션이죠? 델타 펑션. So P is simply given as the P, I'm sorry. This is the distributed load Q, X, now P times 델타 at 여기가 지금 어디예요? 2분의 L이죠? 2분의 L에서 델타 펑션을 쓰는 게 바로 QX다라는 얘기입니다. 자, 여기서 여러분들이 리마인드 좀 해야 돼요. 델타 펑션이 뭐냐? 이게 갑자기 왜 델타 펑션이 나오는지 어쩌고저쩌고. 여기 한번 봅시다. 어, we like to express the A concentrate load P using a say in terms of distribute load. 다시 얘기했지만은 all the derivation or carbonication is now given as a distributed load. 그러니까 폭 곱하기 높이로 해줘야 돼요. 근데 Q는 집중 P는 그게 아니다. 이거 어떻게 해야 되냐? 자, we like to express a concentrated load in terms of a distributed load. What you need to do? Let's say I'm almost sure that it will give us the delta function because the delta function is the way of expressing the concentrate load. Okay. Uh, okay, here. Mathematical representation. If we need a exact point indication, Qx will be P times X. Okay, I mean, sorry, delta is X minus X0. Okay, this is a better expressions. 이게 바로 direct delta idealizer true point load at X0예요. 오케이? 델타 펑션. 아, 지금 자꾸 수학적으로 얘기하고 싶진 않은데 어쨌든 일단은 문제를 풀기 위해서는 델타 펑션 뭐 수학적인 익스프레션을 우리가 활용을 해야 되겠다라는 얘기입니다. 그 이전에는 뭐 어쩌고저쩌고 이렇게 뭐 푸는 과정이 있는데 그거는 우리가 더 잘 풀 수가 있어요. 이것이 지금 중요한 겁니다. Okay, so 그러니까 지금 let's try to solve the pen problems uh, using a force of the carbonication. We can express the concentrate load P we can express the concentrate load P in terms of using the uh, well, okay. Let's try to solve the pen problem using fourth order carbonication. We can express the, I don't need to say actually, uh, let's delete this one. We don't need to teach AI how to solve it. Uh, let's say, please guide us. Try to solve the pen problem using fourth order problems. Then it will say delta function and so on. Uh, they, I mean, we can solve the problem a little different ways. The first order one is very much consistent. The reason I'm emphasizing the first order carbonication is that now all you need to do is that express any load using Qx and then apply the four boundary condition, then you can simply say the all you need to do is just the mathematical solutions, and you will get. Well, it takes some time, more than 1 minute. Well, little weird. We already have okay, I mentioned the pen. See, I'm almost sure that this force of the carbonication is really complete once we know how to solve this one, the beam problem will be solved. Oops, it stopped. Let's do it again. Oops. Man, this guy denied. But the more important point is that you understand the all the carbon equation, and those carbon equation is the combination of equilibrium, material property, and the all the deflection and conditions. Okay, uh, so that is the one I like to emphasize. That is also can be understood by understanding 3+351 flow chart. Maybe my prompt is not so much clear. The That's why it takes some time. I just give a direction that the first order carbon equation. I should say beam equation. I should solve the pen beam problem. That would be make it more clear. Oh, I never seen take this much long. So, okay, while we are waiting, let's continue. So the let's say we have this much too simple support problem, and then the V 4 times will be okay. We got some reply here. See, carbon equation EI instead of V, it says Y QX. Now point load P at span X, this is a delta function because we applied the concentrated load. Now it's given as the QX. This is the one, C QX. Now boundary condition. How many boundary condition mathematically do we need? We need a 4, but physically we already have a 4. At X, Y equals 0, deflection is 0, and then y equal L, the other end, deflection is 0. Now, importantly, the moment at each end also 0. Moment is given as a second derivative. So second derivative will be a 0 at the 0 and L. Now, mathematically, we have a carbon equation. We have these boundary conditions, and for them, that's all we have. Now we have a all equation. Now let's try to solve by splitting span. Well, he took the just a divide, and then this is just one we like to go through. This is all purely mathematical steps and solving this one. Here is the y-x on the left-hand side. Here is the y-x on the right-hand side. Deflection, maximum deflection is given like this. This is a delta, PL3 48EI. And the applied to the span, we just specified the length equal L equal given 200 millimeter, D0, 10, DI, 8. So this moment of inertia is the 2.90 or 290. Young's modulus is now 3 gigapascal. Okay, 3 gigapascal. And then deflection, X is deflection. Put it here and this. And 11 millimeter. Do you remember we already chat GPT expect 11 millimeter. That's the one we get this one. And additionally, it didn't say now what is the maximum stress. Because we already went through, but this is purely going through force of the deflection equation using only boundary condition. So what and where is the maximum stress? Of course, at the center, because the moment will be for your simply supported PVC pan with the center point load apply P and this, and where location at the middle mid-span at the center, okay, and I is given, and sigma x is given this, and then again, this stress will reach yield strength 50 megapascal of PVC. That's why we got the same. The force applied will be 57 Newton, which is approximately 6 kilometer. Okay, 6 kilometer it can support without failure. So this matches the earlier strength limit. Well, this is the how we go through all the equation. Well, this differential equation looks a little bit more complicated than before. Yes, it is, because now, but you will see how powerful it is. All you need to do is just solve this equation, okay? And then a boundary condition. That's it. The other one will be all mathematic, integration and so on. Well, you can practice the mathematical integration, and integration constant can be obtained from boundary condition and et cetera, which you can do that. But conceptually, more important point is that not the mathematical detail, but this is the carbonication and then a boundary condition. This carbonication already took care of the equilibrium, material property, and all strain condition and etc. So this contains all five steps here, and this is the boundary condition here. And so as you can see, Q is the external force, and EI is the material property, Y is the deflection. This is exactly what we are saying in 3. Okay. Okay. So this is the message I like to emphasize today. I hope that it's not too boring. I know it's kind of boring, all mathematics and concept and etc. But at least once you need to understand full steps. Now, next one is that you as a designer, you can design all kinds of the not only